So we're going to start talking about the second part of soil colloids, which is the absorption of cations and anions. As you remember from last time, we talked about the actual structure of silicate clays, which includes the building blocks tetrahedra with oxygen surrounding a silica, and then the octahedra building blocks where we have oxygen surrounding magnesium or an aluminum, and these make up the tetrahedral layers and the octahedral layers. And then we have the one-to-one layers where we have one tetrahedral to one octahedral sheet. And in examples where we have like kaolinite, which is a one-to-one, the inner layer space is hydrogen bonded to the next set of sheets. And so there is no expanding there. Versus smectite, which is a 2-to-1 mineral where it has two tetrahedral sheets and one octahedral sheet, and then a giant interlayer space that expands to take in water and other molecules and miscellaneous cations. Um, we have vermiculite, which is a 2-to-1 that also expands, but not nearly as much, but it can take in some water molecules, magnesium, and other ions. It just does not swell nearly as much as smectite does. We've got fine-grained mica, which is a 2-to-1 non-expanding type of clay because it has potassium in its inner layer space. And so that keeps the different layers of sheets from expanding because it holds them together. And chlorite is another 2-to-1 non-expanding because it has a hydroxide sheet in the inner layer that holds it together. Remember to look back at important terms like isomorphic substitution, tetrahedral layers, octahedral layers, hydroxyls, what deprotonation is. Make sure you understand which ones are pH versus permanent charge. And some of the fun characteristics like surface area and expansion ability, that kind of thing. So as we look at all these pictures, what I want you to start thinking about is that each one of these scenarios, something is being added to the soil that could be adhered to the surface of these clay particle structures that we've been talking about. They can attach to those parking spots that we started referring to as the negatively charged sites, and in some cases, positively charged. Oh, hey, look, it's Captain Jack Sparrow holding a jar jerk. That's exciting. All right, so we're going to start talking about some important ions in soil, some cations that are important, some anions that are important, and the ones that are shown here in orange are actually your plant nutrients. So calcium, magnesium, potassium, sodium, ammonium, iron, copper, zinc, nickel, and then for our anions, we've got sulfate, nitrate, phosphate, carbonate. I mess up chlorine and chloride all the time, so I'm sorry in advance. And then molybdate. Those are all important plant nutrients that are important ions in the soil. And these are all the things that we're going to find parked in our parking spaces on those surface sites. So we're going to start talking about those colloid ion complexes, those parking spaces that I keep referring to. We're going to start defining them further. So we have an outer sphere complex and an inner sphere complex. So first let's talk about the outer sphere complex. Here we have a calcium ion that is hydrated by a bunch of waters. Okay, so it's got like the circle of waters around it. And anytime you have an ion that's hydrated by waters like this, it basically can't directly attach to the surface. Instead, it kind of hangs out, kind of like a Tinder date. Okay, so we've got like this bridge of ions to the colloid, these electrostatic bonds. They're very temporary, they're merely dating, maybe just talking, not even sure, kind of hanging out, nothing permanent. Okay, so that's what an outer sphere complex is. An inner sphere complex is way more dedicated. Okay, there's no water in the way, there's direct or covalent interactions, which are very, very powerful. We're talking like next level marriage commitment right here. Like the potassium in fine grained micas, which were our 2-to-1 non-expandable um, colloids. Sorry, my brain. That potassium in the inner layer was holding them together with the inner sphere complex. Okay, and here in this example, we can see phosphate interacting with an aluminum octahedral layer and creating an inner sphere complex. So it's very difficult to pull this phosphate off this colloid, you're going to have to break an unbreakable chemical bond. So sorry, it's going to be really hard to do. So those are the real differences between our outer sphere and our inner sphere complexes. Okay, so the outer sphere are electrostatic temporary bonds with a water encircled ion that like creates a temporary bridge. Whereas our inner sphere complex is direct and covalent and very, very permanent. Okay, and so here's just showing that again. We can see the outer sphere complexes are just kind of hanging out, and we can see the inner sphere complexes have made a direct link. Now, the problem that we have, especially in soils that have a lot of aluminum or iron oxides, are that when we add nutrients like phosphorus, we get these inner sphere complexes formed in the inner layers and with the octahedral layers. And this basically permanently fixes phosphorus. So you have to overcome the soil's ability to fix phosphorus in these inner sphere complexes before you'll ever get enough phosphorus in the soil to feed the plants. And so this is one of the main issues that we have with iron and aluminum laden soils like those in the top. So what does this all mean? Basically, outer sphere complexes are very easily disrupted. The competing ions can replace absorbed ions very easily, and the inner sphere difficult to displace interactions are really specific, and they're very, very purposeful, and they're very hard to break. So the inner sphere are almost permanent. They're very difficult to displace, and they're very specified. Okay, so there's specific things that like just to bond specific ions. So phosphate is a good example to aluminum. So this brings us to our cation exchange reaction, because ultimately we're talking about those parking spaces as potential exchange sites. What parking what kind of parking spaces are we providing? Are we providing temporary or are we providing permanent parking spaces? So this ion exchange is the rapid exchange between the diffuse hydrated ions in solution and ions on the colloid surface. These are the outer sphere complexes, okay? They're like post-it notes coming in and out as we exchange them for nitrogen or sulfur or calcium or whatever it is that we exchange on those ion exchange sites. It's rapid and it's quick. The exchange complex itself, all colloids in soil, mineral, and organic are capable of ion absorption and exchange, meaning they have these little parking spots on their edge sites that things can come and attach to or detach from. And that is the exchange complex. It's basically the number of parking spots in the garage. So there's principles of cation exchange reactions. There's 6 of them. There's the principle reversibility, charge equivalence, ratio law, anion effects on mass action, and cation selectivity, as well as complementary cations. So let's talk about reversibility first. Exchange reactions are rapid and reversible. Okay, so they occur really quickly and they can exchange and reverse just as quickly. Charge equivalent reactions are where you're going to replace the same number of charges. So in this instance, we've got 2 plus calcium being exchanged with 2 1 plus sodium. So ultimately, we're exchanging 2 plus either way. It goes on a charge for charge basis. The ratio law is where at equilibrium, the ratio of similar cations and exchange sites will be the same as that in solution. Okay, so the exchange ratio here is 4 magnesium to 1 calcium on either side of the equation. The principles of cation exchange reactions for anion effects on mass action basically says that anions or negatively charged ions are always present, okay? The type of anion will influence the direction and equilibrium of the reaction. So if your anion causes precipitation, volatilization, or a strong association, then the reaction is going to move to the right. And just a side note, mass action is basically the reaction, it's just saying that the reaction will proceed to the right if the released ion is prevented from reacting in the reverse direction. So here's some examples of that. In the first example, there is no anion effect. It's fully reversible. But in the second reaction, we have a liming reaction where association and volatilization are largely reversible. We added some calcium carbonate, aka some limestone, because we're trying to lime the soil to increase the pH. And ultimately, what happens is the calcium displaces the hydrogen on the colloid sites and releases CO2 as gas to the air. And those protons, which were making the soil acidic, are now bonded as water, and the pH has been allowed to rise. Complementary cations continued. Basically, this is relating to cation selectivity. Displacement of cation from the cation exchange depends on how tightly it is held relative to its neighbors. So again, we have that selectivity sequence. Sodium is least bound, hydrogen is the most bound. So if aluminum is coming in here and it's pretty much towards the most tightly bound site, it's gonna be really, it's gonna kick off the sodiums or the magnesium or the potassium. All of those are least tightly held, so it can kick off any of those that it chooses. Okay, and so it's probably going to kick off the potassium and the hydrogen and then one sodium, or two sodiums and then a potassium. Sorry, I said that wrong. It's going to kick off the ones that are least tightly bound, so it'll kick off the two sodiums and then the potassium first, because it just has higher ranking than they do, basically. Ranks higher up. So again, reversibility, chemical equivalence, ratio law, anion effects, cation selectivity, and complementary cations. Let's talk about cation exchange capacity. Okay. Ultimately, it's the ability for these negative charge sites on the edges of colloids to provide parking spots for ions, and how easy it is for those ions to switch out. We're going to skip this calculation because it is not important. All right, base cation saturation. As pH increases, the amounts of calcium, magnesium, and potassium and sodium increase. These are our basic cations. They are a relative measure of weathering. So the higher the base saturation in a soil, the least weathered it is. So the less weathering has occurred, okay? The lower the base saturation, the more weathered it is. And this is why ultisols are ultimately weathered, because they have base saturations of less than 35%, which is really low. So we measure base saturation by looking at the percentage of calcium, magnesium, potassium, and sodium ions that are on parking spaces versus how many parking spaces they are, okay? So as we estimate CEC, there's a variety of ways to do it. Most people just take a sample and send it into the lab. But you could also estimate it based on the percentage of clay or humus. You could multiply cation exchange capacity for material by the percentage of the material and then add all the components. I'm not going to ask you to do any of this. I just want you to understand what cation exchange capacity is and why it is important. But here's how you could do those estimates should you want them, but I'm going to skip this slide as it's not something that I'm going to require of you. All right, so the effect of texture on cation exchange capacity. So sands have very little cation exchange capacity. Sandy loams have a little. Loams and silt loams are starting to get a decent amount. Clay loams have a significant amount, and clays have a lot of cation exchange capacity. Cation exchange capacity is measured in centimoles of charge per kilogram of soil. And of course, all of this is going to vary dependent on the types of clay minerals and the amount of organic matter. Those will increase or decrease cation exchange capacity. It's important to understand that in permanently charged minerals, as you increase pH on the x-axis, permanently charged minerals will stay the same cation exchange capacity. Their cation exchange capacity is not going to change with pH. because they're permanently charged. They have a permanent number of parking spots, and it's not going to change when you change the pH. However, the variable charged um, ions, they're going to increase their cation exchange capacity as you increase pH. And I'm realizing as I'm looking at this figure that everything got moved around. This variable charge label should be up here on the graph that increases, and the permanently charged one should be a giant box here on the bottom, so I apologize. Cation exchange capacity is a means of expression. Okay, we express it as moles of positively charged adsorbed material per kilogram of soil. So these units are centimoles charged per kilogram or centimoles charged per kilogram -1, depending on how you want to write it. Those mean the same thing. The range for most mineral soils is 0 to about 70 centimoles charged per kilogram soil, and in organic soils it's significantly higher, from 100 to greater than 150 centimoles charged per kilogram soil, because of all those functional groups. I mean, it's just crazy how much they can pack into them. Anion exchange is basically everything that we've talked about, but instead of for positively charged ions, now we're looking at the ability to displace negatively charged ions on charge sites. Okay, so anion exchange holds to soil colloids in two major ways. So anion adsorption mechanisms are similar to those responsible for cation exchange, or they are due to reaction with surface oxide and hydroxide functional groups that form inner sphere complexes. So anion exchange capacity, they're all going to be outer sphere complexes, meaning they're like hydrated with water and have a very weak association with the surface of a clay colloid. There's a very small amount of this. Colloids with pH-dependent charge are important for this, like all aluminum and iron oxides, because they're the only ones that basically can develop a positive surface charge. Most soils have a negative surface charge. So if you have a negative surface charge and a negative ion trying to attract to it, it's going to repel, right? Because only positives and negatives attract. So in this case, it's only those colloids which are at low pHs and have become positively charged and then can associate with a negative ion, such as nitrate, for example. What colloids do this? Aluminum and iron oxides, one-to-one clays like kaolinite, and we have some examples of acid soils. So ultimately, anion exchange capacity is only high at low pHs because of those pH dependent minerals that are capable of becoming positively charged. Everything else is going to have a positive surface charge, which means, I'm sorry, a negative surface charge. So as pH increases, anion exchange capacity goes down and cation exchange capacity increases. Make sure you understand why. If you have any questions, please reach out to me, and definitely prepare the study guide. This is the harder of all of the chapters. I don't try to make it, it's just people really struggle with the chemistry. So remember, there's an influence of pH here. So here's some inner sphere complexes showing the strong results of phosphorus being bonded. This is a huge problem in acidic soils because then we can't get that phosphorus back. And so we have to overcome the soil's ability to inner sphere complex the phosphorus so that we can provide phosphorus to the plants that we're growing there. I'm going to skip this. In summary, ion exchange is important for the storage of plant nutrients, for providing buffering capacity, for providing adsorption of heavy metals, for providing adsorption of cationic pesticides and other organics, interactions with microbes and pathogens, and soil scientists use cation exchange capacity information to determine the amount of limestone required to raise soil pH, as well as to determine the amount of fertilizer nutrients required to provide adequate crop growth.